Okay, welcome back everyone. So we'll continue with my talk regarding the conformal symmetry in field theories. Okay, so let me review what I talked about yesterday. So I said that the content of this lecture series is about like why we are interested in conformal symmetry, what is conformal symmetry, constraints of this symmetry in field theories, and the recent like progress in this area within the realm of conformal bootstrap program, and and also the most recent developments within this program itself. So, and as I said, I don't hope to cover all of this. We'll see how much we can, but the most important point is to motivate the participants why we should be interested in conformal symmetry. And as I said, I do not expect you to know like QFT, RG formalism, critical phenomena, conformal algebra in general, or like harmonic analysis, things like that. So I do not expect you to know this. We'll be discussing whatever is necessary. And of course, this is a problem if you are already an advanced physicist in this area, so my apologies, as I said. And I also told that we have this Slack channel where I share my notes, some relevant things. You can always ask questions there, initiate discussion, etc. So I'm repeating this because I know at least some people were not able to attend yesterday, so I want to, review what we talked about yesterday. And you are welcome to initiate discussions. Lastly, I also will not be citing any sources, so please see my notes. And lastly, these lecture series are all about higher dimensional conformal symmetry, like in 3 dimensions, 4 dimensions. I mean, when we say higher, people usually think of like higher than 4. That's not what I mean. Like we are interested in not 2D CFTs because 2D CFTs are special that you need to analyze Virasoro algebra for them. Okay, good. So let me also review what we talked about in general. So we said, okay, we start with something very basic that we all know, that fluids have phase diagrams, right? And phase diagrams are basically these schematic things where we have axes of phenomenological parameters like thermodynamic quantities. They don't have to be thermodynamic, by the way, but in general, like this is temperature, this is pressure, and fluids have this diagram that we all know. Here it's solids, liquid, and gases. And we observe that we have these lines that divide the phase diagram into different regions, and some of them end at some points, and these are called the critical points. Okay, so which will be important for field theory. Likewise, magnets also have phase diagrams. In this case, one of the axes is still temperature, but the other axis is external magnetic field. So if you apply a magnetic field externally to a magnet, it will magnetize. So we all know that that's the property of magnets, that they magnetize, right? They are what's called being ordered. So they're like if you think of magnets as millions of small spins at each lattice site, they point at some random directions. If they point together, then there's an overall net magnetic field. There's an overall net magnetic, and this is called ordered phase. This is actually what we observe in everyday life, right? But if you're above some temperature, which is called Kerr temperature, they become disordered. So they lose their magnetic properties, which is less commonly known because we do not usually observe this in everyday life, right? And they have this phase diagram. Here they are ordered, here they are disordered, here it is critical temperature. And here in this order, there are 2 different cases. They can be ordered in one direction or in the opposite direction, and there's a phase transition between them. And again, this phase transition ends at some critical point. Good. Now, our goal will be to try to understand these phases and phase transitions. And at the end, we'll see how conformal field theories come into play. And it's not like a specific situation. Like you may be wondering why phase transitions. As I emphasized yesterday, this is just to show some general concepts like spontaneous symmetry breaking or number Goldstone bosons or long-range interactions versus short-range interactions, which we can all understand in this formalism, but which all apply in many different areas, including high energy physics and quantum field theory. So what we'll be discussing here actually are relevant there. Again, I'm just reviewing what we already talked yesterday for your own sake. So we said that statistical mechanics have this master formula. Here, beta is the inverse temperature, 1/T. H is the Hamiltonian, F is the free energy, and the trace means we are summing over all kinds of degrees of freedom in the Hamiltonian, right? And we said that the non-analyticity in this free energy gives the phase transitions. So what we observe here, these are just the non-analytic regions of the free energy. So we need to compute this. And in fact, if you have the free energy, you can compute everything like heat capacity, compressibility, susceptibility, order parameter, etc. Okay. Here's the problem though. H is analytic, it's Hamiltonian, and it's usually analytic. It's just the energy of the system, it's an analytic function. So to get something not analytic out of summing analytic terms, we need infinitely many terms. So if you sum finitely many analytic functions, the end function is also analytic. But if you sum infinitely many analytic functions, the sum can be non-analytic. That means this trace needs to be over infinitely many degrees of freedom. And in statistical mechanics, this is basically thermodynamic limits. So we need to take thermodynamic limits to understand phases and so on. And we also mentioned that this is very hard to do and almost impossible to compute in practice. And in fact, it's sometimes even impossible in theory. And this is related to the undecidable nature of the mathematical problem. We talked about this yesterday. Please see my notes for further things. Okay, so, okay, it's impossible to work with the microscopic theory. What do? We create so-called a phenomenological approach. We say, okay, instead of working with individual water molecules, let's work with the water density field, rho x. And instead of working with individual lattice spins, let's work with magnetization field mx. So in a sense, even though the microscopic theory is discrete, we are forced to consider field theory because we need to use some kind of phenomenological approach to get some results. Otherwise, we simply cannot compute things. So in turn, this means instead of using this formula, we are actually using this formula, the second one, where now, again, it's e to the minus beta f, this is the free energy again, but now we have a path integral over some continuous field. And instead of Laplacian, instead of Hamiltonian, we are defining this Landau potential. Okay, it's a phenomenological thing, we will construct it. So this is the approach to compute things. And again, we discussed this, and I will just review it now. Now, are there any questions so far? I'm moving fast because we discussed it yesterday, but some of you were not here. But at least I know there are some people who weren't here yesterday. So if you have any question, please let me know. And also, please interrupt me during I'm speaking, okay? Don't make me to stop. You may just wait too long. Good. Okay, so that was the idea. We saw that. And the thing is, there is a huge similarity between the phenomenological models in statistical mechanics, like their usage in solid state physics, material science, etc., and those in high energy physics. And just compare these two equations. Like the first one, what we just saw, is the phenomenological model in the statistical mechanics, right? The Z is called partition function. Again, beta is the inverse temperature, F is the free energy, and we saw that it's given like this path integral. And if you don't know path integrals, again, it's fine. Just think of it as the ordinary integral. Now in high energy theory, we instead use this thing, where Z is now the vacuum generating function. W is the generator of all connected Green's functions. Again, we are integrating, we are having some path integral, and the exponent is now action, which we obtain from Lagrangian. Okay, so they basically have the same mathematical formula. That means many lessons that we are learning in phenomenological models of statistical mechanics are directly applicable to high energy physics. And in fact, historically, they were first derived there. Like, again, spontaneous symmetry breaking, RG formalism, mean field theory, non-Gaussian bosons, etc. Like, there are lots of things that are common in both approach. Now, here, okay, we are using fields in both cases, but if you look at, let's say, take water, for example, and let the x be like the length scale. At the very microscopic end, like we had electron field, right? Like I'm assuming we don't have like strings or some high dimensional objects, just standard model. Okay, so at this end, we have like the electron field. It's a field theory. It's a quantum field theory, good. Now, if we go a little bit like atomic scales, now we have a discrete objects like water atoms or molecules. So we need some microscopic lattice theory to describe them, discrete. Now, if we move a little bit up again, we can have a phenomenological model with water density field, rho x, And again, it's a filter. So this filter and this filter shares lots of common things. That's what I was talking about. Good. So in short, we said that, okay, to get the phase diagrams, replace the macroscopic theory with the phenomenological model, assume mean field theory approximation, which means we first assume that the fluctuations can be ignored, compute some stuff, then determine whether fluctuations are important or not. If we determine fluctuations are important, then our original assumption was incorrect, so that means the model is not reliable. But in some cases, it turns out that the fluctuations can indeed be ignored, so the model is self-consistent. For the sake of simplicity, we assume here, let's assume the model is self-consistent. So we can do this, we can just ignore fluctuations. So that means this equation basically becomes this one, right? So in this integral, there's a dominant term here, like the minimum of this thing dominates, right? Because it's e to the minus and beta is positive. So we can approximate this sum, this integral, this path integral, think of it as a sum, with a term which is the maximum one. Here, this L is the minimum. So this value of the phi, which is called order parameter in this case, it's such that L is minimized.
Can I ask a question here?
Please.
Regarding to the previous one. We are ignoring the fluctuations here. Mm-hmm. If you want to compute, where should we look at it? I mean, what is the name of the theory or the mathematical tools? Just asking for references, and not reference, I mean the topic, the name of the topic.
So, okay, so this is Lambda formalism. Okay, what I'm describing. There is a Landau-Ginzburg criteria. So the Landau-Ginzburg criteria determines whether you can do that or not. So you start with the assumption, have a formalism, compute the fluctuations, compute their importance, and that gives you this criteria whether they are important or not. If you find them to be non-important, then everything is consistent. If you find them to be important, that means your initial assumption was incorrect, so you need to start over. But in fact, this whole thing can be derived from dimensional analysis, which we will hopefully talk about. And all of these are in my notes, by the way, including dimensional analysis. And this is highly related to renormalizability of the interactions.
So you are referring to ordinary mathematical objects of the QFT then?
Well, this is doesn't do with QFT. Like, we use them in QFT. Like, for example,
linear numbers, the dimensionalities, I mean, they just remind me those concepts. That's why I said.
Yeah.
I mean, it is the same formalism.
This is the original formalism. We took them from statistical mechanics and we used them in high energy theory. So, like,
order doesn't matter.
Earlier than like usage in high energy theory. This is actually why I'm starting with this. I think these are easier to understand. These are historically earlier, and you don't need to consider like subtleties related to like the Lorentzian. Nothing here is Lorentzian. Everything's Euclidean. There is no subtlety there. Like, you don't need to do with contractions. You don't need to deal with distributions. Everything can be a function, smooth function, etc. So, yeah, these are easy to work with, and they're historically earlier, which is why I'm reviewing them. But you're right. All these concepts, like, for example, we will just go about Navier-Stokes bosons. People usually know them in the context of, the Higgs mechanism or just spontaneous symmetric in quantum fields. But there's nothing quantum about them. You can have them in this setting as well. Okay. So,
thank you.
Sure, no problem. Okay. So, yeah. So, long story short, the free energy is, okay, let me take it back. Yeah. The free energy is the minimum of the Landau functional. Okay, Landau potential. Good. So, but yeah, we said we want to get some non-analyticity to describe the phase transitions. And we can get non-analyticity if the minimum of the Landau potential is degenerate. So if we have multiple minima, then we can get some non-analyticity. Indeed, like, for example, again, like I had these nice diagrams which are in my notes, and we viewed them yesterday, so I will be quick here. But take this potential, for example. Let's say I change some parameter. It becomes like this, and then like that. Now these two minima are degenerate. So we need to choose one of them. Let me choose this one. So there needs to be some kind of phase transition because there's some non-analyticity here. There are multiple minima. I'm choosing one of them. But the thing is, the variation of the minima is smooth. Like it starts from 0, it goes a little bit to the left, a little bit to the left, right? So the minima, the value of minima here, it changes smoothly. So this is called continuous phase transition. But how, consider this case. I start with this function. I change some parameter. It becomes like this. Now these two minima are degenerate. Then I vary it a little bit more, and it becomes like this. Now the minima, it was on the left, jump to the right. This is also a phase transition, but it's not continuous. We see that minima is jumping from one to the other as we change some parameter. So this is associated with the first order phase transition. And in fact, we can see that in this case for fluids, for example, this blue line has a first order phase transition, and this endpoint has a continuous phase transition, as we reviewed yesterday. Good. Are there any questions so far? Is this all clear? What they're talking about? Okay, good. So long story short, yeah, we have these phase transitions, and we can explain them in this Lambda formalism at the very leading order, and we observe this first order and continuous phase transitions. Now, there is something called Ehrenfest classification. I didn't talk about this yesterday, but Ehrenfest classification. So it classifies all phase transitions as first order, second order, third order, etc. This is outdated. It's not the modern way, because so the way it does it, it says some phase transition is nth order if nth derivative of the free energy has a discontinuity. So this is how it classifies. Okay. So for example, continuous phase transitions are sometimes called second order phase transitions because second derivative of free energy is discontinuous. However, this assumes like all non-analyses are discontinuities, which is not true, because there are some cases we get divergences instead, like in heat capacity, for example. So this doesn't capture everything. Instead, the modern way to do them is like roughly divided in two groups, first order and continuous. Okay, there are some other cases as well, especially in 2D, but roughly this is better. Good. So far, so good. So we can say, okay, what can we observe at this critical point? We saw that there's this phenomenon called critical opalescence. The transparent fluids became opaque. Like they had this milky view that you couldn't see through them. I actually shared a video of it, like experiments showing this phenomena in the Slack channel. Please check that. But why? That's the question, like why do we get this opalescence? And the explanation is that the fluctuations become scale invariant at the critical points, meaning that there are fluctuations in all kinds of scales, all kinds of frequencies. So any frequency of light basically gets scattered. Okay, all light basically gets scattered, hence making the substance opaque. So that's like the experimental indication that we may have. Historically, this was, I guess, 100 years ago, early 20th century. This is how people start to think that, oh, maybe we should consider scale invariance. Because they had this experimental evidence that, okay, something's going on, something is becoming opaque, and they start to consider scale invariance. And that's how it started actually. Okay, good. Now, we can say, okay, how can we understand this scale invariance in a mathematical setting? Then we consider this object. Now, in this talk, this is like Dirac's bracket notation. I will be abusing the notation. I will use this for many different things, which are very related actually, but like correlation functions, two-point function, Green's function, propagator, like these are all basically denoted like this. Some of them are synonyms, some of them are not, but yeah, it's not really important. Here, for example, I'm using this as a correlation function of the field phi, which may be, for example, density of the water. Okay. Now, so the fluctuations in density of water are correlated like this. The general form. They usually go like a power law times some exponential term, some exponential suppression. And this coefficient here is called correlation length. Okay. Now, that can be two different cases. First case,
can I ask you a question here?
Please.
How do we calculate the mathematical object inside the so-called Dirac brackets?
So, okay, it depends on like, okay, if this was like a time order product, So let's take quantum field theory. Okay, in Lorentzian signature, for instance, it's the time order product.
Just like path integral then.
Exactly, just like path integral.
Okay, then that's all I wanted to know. Thank you.
Yeah. But it's complicated because we are Euclidean signature now, so it's actually Euclidean ordered. So in Lorentzian signature, the order is ambiguous. You can change the order of different things. So you can have different orderings. Like time ordered is like the most common one, but you can always choose different orderings by choosing different epsilon prescription. We can talk about it later, because that relies on the fact that things in Lorentzian signature aren't defined as functions, but as distributions. So we have this kind of freedom. In Euclidean signature, that's not the case. There's only one order that makes sense, and that's called Euclidean orders. And I am just glossing over these details because they're not relevant for the main discussion, but we can talk about them later if you want, like in Slack. Okay, or maybe later during discussion at the end of the day. Good. Okay, so there are two cases for the correlation length, right? It can be finite or it can be infinite. Now, if it is finite, that's called a short range interaction because this correlation dies off exponentially. It doesn't really reach far out. So the interaction that causes this correlation, because if they're correlated, that means they share information within each other, right? The operator at position X and the operator at position Y are sharing information, like they're exchanging information so that they can be correlated. And that information is like because of the interaction. And if it is exponentially suppressed, we call it short range interaction. And if the psi is infinite, then we call it long range interaction. And in the field theory context, in quantum field theory especially, that means we have a massive particle in the case of short range interaction and a massless particle in the case of long range interaction. Basically, mass goes like 1 over psi. Okay. Now, as examples of this are like the quantum electrodynamics. We have photon, it's a long range interaction, and quantum flavor dynamics. We have W and Z bosons, it's a short range interaction, like weak interactions and electromagnetic interactions. Short range versus long range. Okay. So, okay, let's remember lambda formalism again. We said we have a spontaneous symmetry breaking, which gives massless excitation and long range interaction. And this results in ordered phase. Like this is why magnets have net magnetization. Because if you think about it, magnets consist of all like bunch of atoms. Each has some kind of spin, right? Individual atoms. And they interact, those spins can point in various directions. So if there is no long range interaction, we expect that the spins will be kind of random. Like, okay, there will be some clusters, like because of short range interaction. Like let's say we can expect some like regions of net spin, right? Let's say this has spin like this spin like that, spin like this. Like there are a bunch of atoms here. They are all correlated because there's a short range interaction. But the net magnetization would be 0. But if there's a long range interaction, then we can expect all of the magnets to align with each other. That means long range interaction or the massless excitation is a sign for order. And we observe this in lambda formalism because the value of this minima, actually, this value of x, it's actually the value of order parameter at the minimum. So if the potential is like this, that means the minimum of the potential is at x is equal to 0. So there is no order. Maybe I should have written this as m. It would be easier to understand this. So this is, let's call this m, like magnetization, and this is like m. Okay, I think that may be easier to understand. So we have the magnetization m, and Lm is the lambda potential of magnetization, right? So in this case, the minima is at m is equal to 0. So there is no order. In this case, minima is here or here. So there is order. M is either, M is either plus minus some value. M not. Okay, so all the spins are ordered. Now, try to view this as a counter plot, right? So let's say this is maybe I should write this as like m in x direction, m in y direction. Okay, m in x direction, m in y direction. Okay, good. Now for this potential, if we view it as a counter, like there's the minima here, and there are a bunch of circles, right? This is a counter plot. Like each circle corresponds to a different value for the potential, like 0, 10, 20, so on, right? And this is the minima, and there is no way we can move. Like the minima is just a point. If we move, we change the potential. So there is like a potential barrier. But in this case, which is also called Mexican hat, the contour plot is like this. Now minima is here, this red circle. If I move like, oops, sorry, this red circle, if I move like this, like radially, it still costs energy. It changes the potential, right? But I can move like in this direction, like within circle. I'm still at the minimum. That means I can move without changing the potential. And that is the effect of massless excitation. And this is called number-Goldstone boson, because this minima now has a dimensionality. So massless excitations of this form are called number-Goldstone bosons, which is actually the same bosons that Higgs mechanism creates. And these are like eaten by the gauge fields, giving gauge fields mass, which kind of explains the mass in the universe in standard model, so on and so forth. But in this context, this is simply just the fact that we can move without changing the potential. Okay, so this was all good. Also, like this mass excitation concept is important in the explanation of rigidity. Like take a solid, for example, try to compress it. You cannot, right? But you can compress gas, right? You can just compress air, but you cannot compress solids. This is because in solids, we have massless excitations. In gas, we don't. So we get from gas to solid phase by breaking the symmetry, actually. Like, so which is why rigidity can be explained by number-Goldstone bosons as well. Okay. Now, are there any questions so far? Okay, I want them.
May I ask, sorry, may I ask one? But
Sure,
it
please.
might be a bit irrelevant. So let me ask it, if it is irrelevant, we may pass it.
Sure.
The form of the correlation function and the topic of interactions reminded me something about locality. Do we have problems about locality here? Or is it a relevant question to ask here?
No, it's a good question. It's a very good question. So, okay, in this description, right, in this Lambda formalism, or in general, I'm doing, let's say, I'm interested in some statistical mechanical problem or some solid state problem or material science, whatever. I am constructing the theory such that these are local objects, right? I can have non-local objects, like non-perturbative objects as well, like instantons or stuff like that. And they are also important, by the way, in some area. But what we have been discussing so far, these are all local fields. Okay, this is by construction. And the situation is similar in quantum field theory as well. They are local objects, but in QFT, it's a bit different because there you have causality. So there's a relation between causality, analyticity, and locality. I don't fully know it, but I guess you can derive one of them from the other two. Like if you accept analyticity and causality, then you can derive locality or something like that. So there's this relation there in Lorenz's signature. But here, we just take it as granted. Okay.
Thank you very much.
Sure, no problem. Another question? Okay, good. Nice. So, so if we go back to critical phenomena, we said, okay, the thing is that the correlation length becomes infinite at the critical points, which we can parameterize like this. The small t is called reduced temperature. It's basically temperature minus critical temperature divided by critical temperature. So at t is equal to 0, the small t is equal to 0, xi becomes infinite. But the question is, how does it behave around t is equal to 0, right? So, and we observe that it behaves like this, regardless of the microscopic theory. Now, that's an important thing because we have lots of different things like magnets, mixture of fluids, polymers, just ordinary fluids, anything. Like they have different microscopic theory, but all of them have this behavior. The correlation length behaves like a scale, like a power law with these coefficients. And in fact, these coefficients called critical exponents are same for different theories. Like if you consider water, carbon dioxide, nickel magnets, like a bunch of different stuff, they all have the same numerical value for this nu. Like this was the surprising thing. This is actually what's called universality that we mentioned yesterday. We just mentioned it, but we didn't really motivate it or derive it. Today we will talk about this by RG formalism. But this is the backbone of the importance of CFTs. This is a universal phenomenon, a critical phenomena. This behavior that we observe, it's universal. We observe it in everywhere, all critical stuff. Like for example, if you consider QCD, quantum chromodynamics, right? Like you can have a phase diagram for QCD as well. There is the baryon chemical potential, and there is the temperature. This is for QCD, right? Just consider quantum field there. And we expect a phase diagram here. We expect it to end the critical line here where QCD becomes conformal. At that point, if we were to compute such stuff, then we expect them to have this behavior as well. So this is universal. And that's really good thing about it. And if we can derive this coefficients, these exponents, then we can explain many things at once, which is why we are using CFTs, because we will see that deriving these exponents is equivalent to understanding operators in conformal field theories. So if a CFT explains this critical point, then the operators at that critical point can give you the values of these exponents. Okay, that will be why they're important. And this is not just for this critical correlation length, by the way. We have many thermodynamic quantities that exhibit this divergent behavior. Okay, so it's better if we just go to notes now. Before we move on, are there any questions so far? Like why this critical exponent business, which I will detail now. Okay, good. So, okay. I think it was here. Okay, yeah. So, good. Now, so I gave some examples here. For example, specific heat, like how temperature changes by introducing some heat to the system. Or compressibility, like if we change the pressure, how a fluid would compress. If we change the external magnetic field, how the magnetization of a magnet change, its susceptibility. Like compressibility, susceptibility, specific heat, these are all that can be measured in experiments. And these all have this behavior that they go like power laws with some universal exponents. And these are called critical exponents, okay? So for instance, like there are these examples here. There's a bunch of different fluids. Now they all have different critical temperature. They have different critical density, but all of them have exactly these critical exponents. Same, doesn't matter. And these are the same critical exponents you would get for magnets. And these are the same critical exponents you would get for 3D scalar field deformed by phi to the 4th theory, which is this 3D Ising CFT. Okay. And actually, that's how we will be computing this. Good. So in summary, so this was like a summary of yesterday, what we talked about yesterday, and a little bit more. So in summary, we talked about the phase diagrams, we talked about the non-analysities, that these correspond to phase transitions that we can divide as first order continuous. And here you can see, for example, this divergent behavior. You see, if you fit this data, if you fit it like t to the minus alpha, let's say, we can compute this alpha, and this is the same alpha for all of these magnets at their critical temperatures. Like again, all of these are same with all of these, like everything, same exponents. Okay, good. So this is the origin of universality. This is the result of universality. And we will try to understand it by reviewing RG formalism. Okay, good. Any question before we start talking about RG flows. Good. Okay. So I will be reviewing it very briefly, glossing over details. Nothing will be rigorous here. So the main thing to motivate why we consider RG, what exactly is it, and how it is useful. Okay. So I won't be doing anything detailed. So here's the idea. We said that we have a phenomenological model, let's say. We write down, by the way, I keep saying phenomenological model, and you may think that this is something special. It is not. Actually, there is this thing called decoupling principle. And it says that, it goes as follows. I think this is an important point. In QFT, if you have a heavy particle, let's say you have a particle with a very heavy mass, you can always integrate it out. You can freeze its propagator, integrate its contribution out. And its existence in this world, its existence in the model is reflected by different values for coupling coefficients of light particles. Okay, maybe this was not really easy to understand, but my point is this. Let's consider two models, M1, M2. M1 has 3 light particles, L1, L2, L3, and 1 heavy particle, heavy 1. And M2 has 3 light particles only, same light particles, L1, L2, L3. Now, if you are at low energies, you cannot distinguish these two theories. You can never know whether this is the correct theory or this is the correct theory, because the effect of the existence of this heavy particle can be absorbed into coupling coefficients of these light particles. So they will have different coupling coefficients, sure, but they will explain the phenomena nevertheless. So this is called decoupling principle. It basically says that you can never know whether there's a heavier particle or not by doing low energy experiments. This is why we are doing all these experiments in the LHC in the first place. Like, we need to go higher energies to probe high energies, because by low energy experiments, you can never know it. In turn, this means that any QFT is actually an effective theory. It's only effective up to some energy. Now, because we can't prove it otherwise, you cannot guarantee that a model is complete. There can always be heavier particles. So that means basically any model is phenomenological. Like, any model is basically phenomenological because it may need to be modified at higher energies. Like, this is the case. In these cases, what is special is we already know that there is something in microscopic theory, we just ignore it. Okay, that's the only difference. In high energy, we don't know. So we take them as there, like the standard model. For example, the QED, like the Fermi's weak interaction. So Fermi write down a theory to explain weak interactions by four Fermion theory. Okay, he write down the theory to explain weak interactions. So that's a non-normalizable effective theory, which works at low energies, but which doesn't work at high energies because we need W and Z bosons. So he doesn't have them. Nevertheless, even without these bosons, his theory works well for low energies. And that's the point. So this was a phenomenological model. It's a phenomenological model because it doesn't take into account the degrees of freedom in microscopic details, like this W and Z. Well, he did this because he wasn't at that time, he was unbeknownst to these particles. Nevertheless, the effect is the same. So whenever I say phenomenological, do not think of it as something bad or special. Like, basically, all theories are phenomenological. It's just whether we may not be aware of it now, but we may learn it later. Good. Any questions about this? Okay. So we said, okay, we have this model, right? Good. And we said that we are writing this. This phi is, let's say, density field for the water. It's a continuous field. Now, it should be valid only at some length scale, right? Like this phi x, for example, can be valid at 1 micrometer, but it shouldn't be valid, let's say, in 1 nanometer. Like when you go down scales that you have individual atoms, individual molecules. At that length scale, this theory shouldn't work because it assumes water can be explained by a continuous field, which is not true if you look at the atomic scale, right? So it's called coarse grains below a certain length. So it integrates out all the details. It ignores all the details below a certain length. And in this case, let's call it like 1 micrometer. Okay. So we assume, okay, this integrates out all details below 1 micrometer. Good. Now here's the thing. The critical phenomena that we observe that happens at quite microscopic lengths, right? So for example, in fluids, the critical operations, it happens at microscopic lengths, like 1 centimeter or 1 millimeter or whatever. So actually like a 10 centimeters, something like that. For example, it's a huge thing that you can observe. So it really wouldn't matter whether we coarse grains below 1 micrometer or below 1 millimeter. That means if I start with this theory, which was coarse grains below 1 micrometer, and change it so that the coarse graining is above 1 millimeter, right? So there are some details between 1 micrometer and 1 millimeter. I am integrating them out, like integrate details. So I'm getting rid of the details, okay? I'm changing it from 1 micrometer to 1 millimeter. This shouldn't really affect anything because critical opacity is like a very microscopic thing, right? So instead of 1.11, I am writing like this. Now, instead of using phi, I am doing it with like phi L, because I decompose all functions, I separate all functions phi x into 2 parts. Ones that fluctuate above 1 millimeter, let's call them phi L, and those which fluctuate between 1 millimeter and 1 micrometer, call them FH. H is like for high frequency, L is for low frequency. So I decompose all the functions into high frequency ones and low frequency ones. The ones that fluctuate rapidly, like below 1 millimeter, and the ones that fluctuate slowly. And I integrate, I get rid of all the high frequency fluctuations. Okay, so I can write, everything is mathematical here, by the way, there's nothing fancy going on. I just write this as, okay, I just write this as this. Okay, now, but you see, the first formula is almost same as this one. It's just instead of phi, which fluctuates above 1 micrometer, I have phi L, which fluctuates above 1 millimeter. Okay, and this L, now the lambda potential, became L prime. It doesn't have to be the same potential, right? It's different. And in fact, mathematically, this L prime is given like this integration. So it's the integration of high frequency modes. Okay, good. So I integrated the high frequency ones, obtained this new potential, and I'm using this new potential in this pattern integral. Is this clear what I'm doing? Any questions? Okay. That means this e to the minus fk can be written either as an integral over 1 millimeter with functions fluctuate above 1 millimeter, or another integral with 1 micrometer, above 1 micrometer, with functions fluctuate above 1 micrometer. Actually, it was the other way around, but anyway. So that's it. And the only difference that instead of, in one case, in one case, I had L, K, phi, and in the other case, I had L prime, K, phi, L, like low frequency mode. But if this lambda potential is including all the terms which have the relevant symmetries of the Hamiltonian, then this L prime shouldn't have any new terms. These should be these should be again the same terms that we already had in L. So this is just L, the same L, with K prime phi L. Okay. So the change would be in these coefficients K, the parameters, the phenomenological parameters, or in QFD called coupling coefficients. So, but this 1 micrometer or 1 millimeter thing is independent. Like I could choose anything, 10 micrometer, 15 micrometer, whatever. So in short, I can write this function as this path integral. Now, it's coarse-grained above some scale lambda, arbitrary, and these coefficients k are functions of lambda. Okay. So that means, and these coefficients are like phenomenological coefficients, like compressibility, pressure, and temperature. These are coefficients like this in standard mechanics. And in QFT, these are like mass, interaction, etc. Like for example, m squared, the mass square would be like k. So we see that mass square, mass is a function of lambda. So mass of a particle, it depends on how you coarse-grain. And actually this is true in QFT. Like when you say, oh, mass of the electron, or mass of this, mass of that, these are not constants. Like mass of a particle depends on how you regularize your theory. Actually, this is why they're called running coefficients. Like you can change, the mass changes with the scale you look at things. So this is all true in QFT as well. Anyway, so that was the main takeaway, that in our model, we can choose an arbitrary scale here to coarse-grain, and our coefficients are functions of that parameter lambda. Okay. That's good. Now, so what happens when we take lambda to infinity or lambda to 0, right? So if we try to take lambda to 0, that means basically that I am not coarse-graining anything. I want to include all interactions in any frequencies, right? But to do that, you need to know the microscopic details, right? So that means when you take lambda to 0, include all frequencies, all interaction, all fluctuations at any scale. And we need to know the microscopic theory to do that theory. So our phenomenological model breaks down. Okay, so we cannot take lambda to 0. In QFT, in statistical mechanics, you cannot take it. Usually, lambda only goes to, the minimum of lambda is like A inverse, where A is lattice spacing. A lattice spacing. So in statistical mechanics, like you cannot consider higher and higher frequencies because there's a limit to detail, and it's usually lattice spacing in statistical mechanics. In QFT, you don't have a natural parameter, right? Like if you don't count like Planck mass or like Planck scale or anything like that, I'm talking about gravity, by the way, just standard model. Technically, you should be able to consider it, right? You should be able to go to 0. And it can, or it cannot. There are two cases. We can do it without, or we can do it consistently, or we can not do it consistently. There are two cases. When we say consistently, it's because we actually get infinities when we take lambda to 0. So it really depends whether we can get rid of the infinities or not. That's the whole issue. So if we can get rid of them consistently, then they are called renormalizable. And if we cannot do it, then they are called non-renormalizable. Okay, whatever. So that's the thing. So that like how much we can consider our cutoff or regularization parameter can we take it to 0. This is, by the way, actually maybe I should write this as lambda minus 1. Okay. So lambda is like cutoff in momentum space. So whether we can take lambda minus 1 to 0, meaning that we can consider all details in position space, or all high frequencies in momentum space. Okay. So whether we can do it or not depends on whether the theory is renormalizable or non-renormalizable. Okay. Now, here's the problem though. If the theory is non-renormalizable, that means it's just a temporary model in the sense that it works for low energies, but it needs to be changed at high energies. For instance, as I said, Fermi's weak interaction, like Fermi's theory of weak interactions was, by the way, sorry. So, okay, yeah. Fermi's theory of weak interactions was a non-normalizable theory, meaning that it was known that it had to be changed at high energies. And QED today is a renormalizable theory, meaning that it is consistent. But that it is consistent does not mean it's true. So it only says that we can go all the way up to high energies, but its predictions may not be correct it may not match the experiments. So that's the problem with renormalizable theories. You don't know whether they will break down or not unless you do the experiment. With the non-renormalizable theories, you already know they will break down, and you can estimate, you can compute, like for example, for Fermi's theory again, Fermi, it was computable that it was supposed to break down around 300 GeV. So the theory itself says, okay, look, here is the model. At low energies, it goes well. Above these energies, it will not work. So the model itself tells you its validity in non-renormalizable theory. This is a good thing, actually, they tell you. In the renormalizable ones, they don't tell you anything. They say, okay, we are consistent, keep using us. And they may turn out to be correct or not. You don't know unless you do the experiment. And since all theories are basically either renormalizable or non-renormalizable, that means all theories are, in a sense, effective field theories, because we really don't know whether they will work or not. Like there's no one class of theories that they're guaranteed to work. Good. So that was the case. How about if I take lambda inverse to infinity? Sorry, lambda inverse to, yeah. So we took lambda inverse to, hold on. So lambda is like a length scale, right? It's a length scale. So let me actually use it like this. Lambda is length scale. Lambda goes to 0. Okay, let me use it like this. Then lambda goes to infinity. So that means I am coarse graining everything. Like I am getting rid of all details. Okay. Earlier I was saying I am getting rid of details below 1 micrometer or 1 millimeter, right? 1 micrometer or 1 millimeter. Let's assume I am getting rid of all details. This is called going to IR. So I am going to IR. Actually, I'll be flowing to IR. And this will give me the IR behavior of the theory. That's what it's called. And most theories at IR are scale invariant and even conformal invariant, which is why we care about conformal field theory. Okay. So this change of parameter thing is basically the backbone of renormalization group flow. Like it's more complicated than that. You change the scale, you do a rescaling. And this is, by the way, the position space coarse graining. There's a momentum space version of this, but it's the same idea. Okay. So that's that. And we analyzed this, we said this coupling coefficients Ki was function of lambda, right? The length, the regularization parameter. We analyzed them. We check how they change as lambda goes to infinity. So as theory goes to IR, for example, or as lambda change. So this is kind of important thing. Let me be clear here. Let me just show this. For example, this is the model, the mu phi square 1/2 plus m square phi square plus lambda phi to the 4. So this is the Lagrangian. Okay, delta phi, something like that. In 3D, in d is equals 3. Okay. Actually, you know what? Let me just keep d generic. In d is equal to 4 minus epsilon. Okay. So take this theory, for example, right? This is just a scalar field, a scalar quantum field in d is equal to 4 minus epsilon. And I'm taking it to be Euclidean. Okay, let's take it to be Euclidean. So this theory, for example, has the coupling constant m square and lambda, right? Earlier I was writing the lambda function as k and phi, right? So here k is either m square or lambda. That means this m square is function of this regularization scale, coarse graining scale. So if you take any point here, let's say, let me just take this point, it has some m square value and lambda value. Oh, sorry. Let me take this point. Okay. Now, as I change lambda, as lambda goes to infinity, this point goes to here, then here, then here. So this is actually the flow diagram of these points. So it's the flow diagram of how m square and lambda changes as I change the coarse graining. This is called the RG flow. Okay, so RG flow is basically how the coupling constants change with scale. Now, if you are here, you will go here, you will go here, and so on. Now, here is the thing though, is you can see there are 2 points here. One is here, and the other one is here. And if you're at that point, you don't go anywhere. So you stay at that point. And these are called fixed points. Fixed points. And if you're at a fixed point, that means the correlation length has to be either 0 or infinity. Because correlation length goes like, let's say, k times psi under normalization growth, where k is some parameter. Okay, so for psi to be invariant under RG, it needs to be either 0 or infinity. And as a corollary of that, any critical point has to be a fixed point of RG, because critical points have the correlation like infinity, right? So if you're a critical point, you have to be a fixed point. So if you know the fixed points of the RG flow, if you analyze the theory, how its coupling coefficients change with the scale, you can then predict where there will be critical points and how they will behave. Okay, so this is like the mathematical formalism to understand the critical phenomenon. And basically, this is not just critical phenomenon. Like any QFT, basically, you need to write down the RG flow to, if it is strongly coupled. If it's a weakly coupled, just forget about it. Do some perturbation theory, which is what we do, like QED, for example. But even then, as you go to strong coupling regime, because the coupling constant changes, think about, for example, QED, right? It's weakly coupled at these energies, like at ordinary everyday energies. If you increase the energy, like if you go to Planck scale, then the coupling constant changes as well. After a certain point, after a certain energy, it will be too high to do perturbation theory. So actually, you need to know this for any QFT. And when I say go to high energies, it doesn't have to be like doing experiments in LHC. Like think about cosmology, like early times of the universe. If you want to understand like how photons behave at the early times of the universe, you need to understand how their interaction was at that time. And then the coupling constant was high. You cannot do perturbation theory. So you really need to understand this stuff for any QFT, basically. Are there any questions so far about this RG flow business? So let me recap for simplicity. It's very simple. If I have a theory, I kind of need to coarse grain below some length scale. Like I need to forget about like details of some length scale, right? For any theory. And as I change that length scale, the coefficients in my action, like this m square or lambda, or like pressure or temperature or anything, it depends on whether it's statistical mechanics or QFT, these change with the length scale. And if I make a diagram of how they change, that's called like RG flow, because I observe like flow of these points. Okay, so far so good. And there is always like not always, but I guess it has to be always, I'm not sure, but at the origin is a fixed point. It's called Gaussian fixed point, because basically if m squared is 0, lambda is 0, like just there is no these terms. It's just like this, and it's already scale invariant. Like it's just it's a free theory basically, and free theory is usually scale invariant. So there's the Gaussian fixed point. If you are free, you remain free. If you're exactly free, you remain free at different scales. And there is this fixed point called Wilson-Fisher fixed point, and this fixed point is explained by the CFD 3D, actually the Ising model or Ising CFD. So Ising CFD explains this critical point. So this CFD explains all the data about like, the heat capacity of the water, susceptibility of the Ising magnet, so on and so forth. Like, I showed all this table with a bunch of different materials like, carbon dioxide, deuterium, blah, blah, blah. So their critical behavior are all explained by this Ising CFT, which explains Wilson-Fisher fixed point. Okay, so I have like 15 minutes. Let me look. So these are all fine. By the way, you may be wondering why I considered D is equal to 4 minus epsilon, right? So why the space-time dimension? It's not like 4 or 3, but 4 minus epsilon. There is a reason for that. As I keep saying every day, we don't know how to work with the strongly coupled theories. And we don't know how to do this RG flow for them either. Like, we really don't know. So the thing is, like one thing we can do is that this, if D is equal to 4, basically Gaussian fixed point and this Wilson-Fisher fixed point are on top of each other. So this Wilson-Fisher fixed point actually is just at the origin as well. Let me just draw it like this. So like here, there's the Wilson-Fisher here, here, here. So it moves like this. Let's say this is epsilon is equal to 0.01, epsilon is equal to 0.1, epsilon is equal to 0.5. You get my point, right? So this Wilson-Fisher fixed point gets away from the origin as you, and dimension is 4 minus epsilon, okay? So at D is equal to 4, there is no Wilson-Fisher fixed point. It's the same as Gaussian fixed point. And at D is equal to 4, Gaussian fixed point is sufficient to explain everything. You know, earlier I was saying we are using this Lambda formalism, and you can compute these critical exponents with the Lambda formalism. They are valid as long as the critical point is the Gaussian fixed point, which is the case as long as D is equal to greater than or equal to 4. So Lambda formalism for this particular case actually only works if D is 4 or higher. It doesn't work at D is equal to 3, for example. That means fluctuations become important at D is equal to 3, which means D is equal to 3 fixed point is strongly coupled. So you cannot use perturbation theory, you cannot use ordinary methods, there is no way to do it unless you do some approximation, okay? And one approximation people often do is to this trick. They consider D is equal to 4 minus epsilon, assume epsilon is very small, compute stuff, then take epsilon to 1. So that's the procedure. Basically, this is called Epsilon Expansion. Now it's ridiculous, right? It's ridiculous because you assume epsilon is very small, then at the end you take it to be 1 because you want to explain D is equal to 3. Now it's ridiculous, but it works, by the way. It works really well. And there are some techniques like Borel summation to improve the data. Like there are some mathematical techniques to make sure this kind of works. But at the end of the day, there's an asymptotic expansion. So it really doesn't work. Like, we're gonna improve it by adding more terms. Like in a convergent expansion, if you add more terms, it becomes better. In an asymptotic expansion, if you add more terms, you don't know what it will be, whether it will be better or worse. So it's really like a gamble. But people do that. It's been working. It's something traditional. And it's really helping us. And we are basically doing it because we don't have another choice. At least we didn't have, unless conformal bootstrap came forth. Like, I'm sorry, until conformal bootstrap came forth. Like the whole point of this bootstrap program is that we shouldn't be using this. Like there's epsilon expansion, there's large N expansion, etc. Lattice simulations. They are good, they're really good, but they're asymptotic, so there should be something more rigorous. And that's the point of conformal bootstrap program that has flourished in the last 2 decades. Actually, just last decade. Yeah, good. So that's the point about, I really wrote down a bunch of nice, well, at least nice for me, but details, some subtleties. I'm not gonna go over them. So, but I guess let me recap this. So we cannot solve a couple theories. And okay, sorry. So this is what I said. We don't know how to solve them. We can try to solve them in lattice, lattice simulations, but it really doesn't. You need lots of computation power. Even then, the problem can be very hard. I said yesterday that this 3D Ising model was NP complete problem. That is this fixed point, this Wilson-Fisher fixed point. So solving this on lattice is an NP complete problem. it's very not feasible to do this in our lattice. Okay, what else? So as I said, like we can solve free theories, so we can try to approximate to free theories. Like one way is the epsilon expansion, as I said, take dimension as like 4 minus epsilon, take epsilon to be small, do computation, etc. Another thing to do is so-called large n expansion. So the way it works is as follows. Instead of working with phi x, I assume there are n copies of it, n copies of phi x. So I assume there are n scalars instead of one scalar, okay? There are n scalars, n of them. And it turns out, in most of the case, if n is infinite, the theory is free. And I know how to solve free theories. So I expand around n is equal to infinity. Okay, so I start with n copies, expand, take n is equal to infinity, expand around n is equal to infinity. Then at the very end, take n is equal to 1. Okay, and this is the large n expansion method. It works with, like, for example, if you consider like QED3 with flavor group SU and F, where NF is like usually taken as 2 or 4. You can do right now. For example, we are actually writing a paper. It's similar to this. If you consider a theory like this, for example, quantum electrodynamics in 3 dimensions with a flavor group SUN, NF is usually 2 or 4. Okay, you can take NF to be infinite, do some computations, like people have done this there in literature, and at the end take NF to 4, like, and hope that it's fine. It kind of works though, but not really a convergent expansion. Okay, that's it. So today we saw that like this is RG formalism. Any critical point is actually a fixed point, and we actually can classify fixed points. Like there's a nice table here I wrote down. You can check it if you want. But let me just say this before I have like 7 minutes. So if I have a fixed point, there are 3 cases, basically. Xi can be 0. So the theory is topological at IR. Xi can be infinity. The theory is free at IR. Xi infinity. The theory is scale invariant, but not conformally invariant. And Xi is equal to infinity, and theory is conformally invariant. Okay, so there are basically 4 cases for fixed points. Now, when I say topological, it basically means that there is no massless degrees of freedom in the theory. So if you are like, if you go to like the very, very low energies, you don't have any degrees of freedom left, because all degrees of freedom are massive. If you are at very low energy, let's say the lowest mass is, 1 GeV. If you go to like 1 kilo eV, 1 kilo electron volt, then you cannot really excite this particle. It's very heavy for you, so it will just freeze. So you will not have any degrees of freedom. So you call that a topological theory. No degrees of freedom left. If Xi is infinite, then the theory can be free, right? Like the Gaussian fixed point. It can be scale invariant, but not conformally invariant, or it can be conformally invariant. Now, many, if not most interesting case are this one. Okay, so we really get conformal invariance. Now, to my knowledge, there is no rigorous proof that like they need to be this. And we have examples that it can be scale invariant, but not conformally invariant. There are examples of this, but there are like really, really nice reasons why we don't expect that much. So you can take most of the time that if we have a fixed point, and if it is not free, if Xi is infinite, it's probably conformally invariant. Okay. In these lectures, I will take it as an assumption. I will motivate it, but take it as an assumption. But this is the case. Any questions?
I have one. May I ask it? If there is another one, okay. But it might be trivial or irrelevant or maybe foolish. But let me ask. So we say that the fixed points can be found at 0 and infinity, right? So, is there a chance or mathematical possibility that it could be at, for instance, complex infinity? Is this possible, or I mean, I'm not sure. I'm not sure how to tell or paraphrase, but
correlation length is supposed to be real.
Real, right?
Right.
Okay.
It needs to be a real number. I guess mathematically you can complexify it. Sure, we can consider complex numbers. I don't see any problem with that. But I don't know what would be the physical interpretation of it. Like you can do that, sure. And like this it can be complex. Like the only reason this is either 0 or infinity, it's not really something sophisticated. It's very clear. Like psi goes to lambda times psi. If you take this, actually, let me just call it maybe k times psi. If you take the cross-graining from lambda to k times lambda, right? So when you do the cross-graining, when you like earlier I was saying instead of 1 micrometer, I was doing 1 millimeter, right? So k is like 1000 in this case. So psi goes to, actually it's the k inverse, sorry. So psi goes to 1 over 1000 psi. If I go from 1 micrometer to 1 millimeter, okay? So it goes like this. And I say, okay, I want it to be invariant, so I want psi is equal to k inverse psi. And it's only possible if psi is either 0 or infinity. That's it. I mean, that's the only reason why we say it's 0. Like, it doesn't matter if it's complex infinity, real infinity. It can be minus infinity. Like you see, if you put minus infinity, it still works. No problem.
Yeah, it still works.
Yeah,
that's correct. But I was curious about the extra possibilities or things that if we introduce.
There are things called complex. There's something called complex CFTs. Slava Richkov has some nice papers about it. But I don't think this has to do with it. Like I see. I just think of them because they are like some stuff become complex there. But I still think this is still real. I believe. I'm not sure. I don't know. One needs to check.
Okay, thank you very much again.
No problem. I have 1 minute left, so okay. So I think this is enough for RG flow. I guess tomorrow we can talk about the dimensional counting, this stuff, like operators are relevant, irrelevant, etc. But long story short, we have many phenomena in like stat mag and condensed matter, etc. So on, and they're all very related to high energy physics, like we observe spontaneous symmetry breaking, Gaussian bosons, this critical phenomena. Like as I showed yesterday, where was it? Like this is the phase diagram for QCD. I already showed. It's very similar to phase diagram for fluids. It's schematic, by the way. It's not full or rigorous, but like the same thing. There's a first order phase transition. There's there's a critical point. Blah blah blah. So knowing this stuff really helps us understand the stuff in high energy theory or in standard model or anywhere basically. So yeah, I really made a quick review of RG, but you get the point. We change the scale, how we coarse grain, and with the change of the scale, the behavior of the terms in the Lagrangian, like mass, like lambda, like temperature, like pressure, like the phenomenological constants, phenomenological constants, or like coupling coefficients. Like they are the same thing, by the way. This is the term used in StatMag. This is the term used in QFT, basically. Like coupling constant in the Lagrangian, for instance. If I have something like this, let's say I phi cube, b times phi to 4, c times cosine phi, whatever. This a, b, c are coupling constants. So these guys depend on how we regularize our theory, and they change with it. And the flow of their change determine the fixed points, scale invariant parts, and so on and so on. Okay, so I think this is enough for today. Yeah, I'm 1 minute late already. Are there any questions? Okay, I'm stopping the record.